Okay, next we have Checking a Denotational Semantics of Scheme in Agda by Peter Mosses.
Thank you. So this is going to be a talk with a fair amount of denotational semantics in it. I'll introduce denotational semantics briefly as a recap for those who are not familiar with it. There will also be some Agda, and again I'll try to explain the bits of Agda that I'll be using. So please feel free to ask questions in the talk if there are things I've forgotten to explain. 1975 was a very significant year for you in the Scheme community. It was essentially the birth of your favorite language. I guess it's still your favorite language. 50 years is a long time for a language to remain popular. And I've had great fun, not having previously read the Scheme reports, digging back into them. It was also a significant year for me in that I completed my PhD in Oxford and a pretentious title, Mathematical Semantics, which was the original name of Denotational Semantics, and compiler generation. It wasn't so much about compilers, it was about partial evaluation and interpreters. But it looked like compilers if your machine code was lambda calculus. The final 50th anniversary that I'd like to recall is a sad one. My supervisor, Christopher Strachey, passed away that year. He was 58 years old, which at the time I was 26, and I thought that was really quite an old age, but now I'm 76, and I think a bit differently about how many years he missed. He was a tremendously influential person, especially in the 50s and 60s in the UK and internationally. This paper is dedicated to his memory. You'll find links to his biography in the proceedings, and also there's the Wikipedia page, which is also quite good about it. So I must admit that my primary interest in Scheme is not in using it as a programming language, but actually in its denotational semantics. That semantics is reasonably concise, and it's been remarkably stable since it was first developed by Jonathan Rees and Will Klinger in 1986. But it has some wellformedness issues, as I discovered recently when I started digging into it. Some of them are quite obvious, but others I didn't notice when I first read it, and I guess the people that proofread the standards haven't noticed them either, because they're still there after so many years. I've been experimenting with testing denotational semantics. I tried it first last year in connection with Jens Palsberg's Festschrift, where he had a denotational semantics of inheritance and some verification proofs. I tried formalizing that and found it wasn't actually quite as easy to embed denotational semantics in Agda as I had hoped. But since then, I've tried to make it easier and simplify what I was doing then. So part of the talk today will be to present that shallow embedding. In the paper, the main ingredients of the paper are about the denotational semantics of Scheme, but also about the shallow embedding with using Scheme to illustrate how this embedding works. And then there are the wellformedness issues that the embedding has detected, or that were obvious in any case, and the suggested fixes. Apart from the main ingredients, you can also take some supplements. There's the artifact, which is linked from the ACM digital library page, which has all the Agda code that is used in the embedding. There are also, on the DOI page, there are links to a couple of PDFs. One of them is a listing of the plain code without any comments for those that really like just to read code and not to know what it means. And then there's what is in the Agda community called a literate Agda specification. This is not literate in Knuth's original sense as a web of unordered fragments that can be given in any stage and developed top-down or bottom-up or whatever. It's just an interspersed. Actually, the literate version contains, I think, all of the denotational semantics from the R5 RS standard for Scheme as comments, and then you get the Agda code corresponding to that bit of the standard to be able to compare it locally. Since the artifact was submitted, I've added some code, a makefile basically, to generate a website from the Agda code, which you may find it more convenient to browse online, but of course the PDF is convenient offline or printed. Please give me feedback if you have any complaints about the website. It's an experimental website generation. So let's start off with the denotational semantics of Scheme. And there have been quite a few versions. It started essentially with a paper by Steve Muchnick and Uwe Pleben back in 1980, and where they were comparing Lisp and Scheme, and also mentioned the difficulty of adding eval to Scheme at the time. In 1984, Will Klinger had a very nice paper with denotational semantics of a sublanguage of Scheme and a proof of correctness of a compiler for that language. Then the official standards, starting with the third revised report on Scheme in 1986, up to the present day, so to speak, with 2013, the seventh revised report, all of them except the sixth revised report contained essentially the same denotational semantics with a few extra features like whether lists were mutable or immutable, and a few other minor details like that. The status of whether null was truish or not changed from one version to another. But it was remarkably stable. If you look at the standards, you find that in the denotational semantics, they cite Joe Stoy's textbook. It's actually quite an ancient textbook by now. It's not available as far as I know, except behind a paywall from MIT Press. I'd like to point out that there is an excellent article by Bob Tennant, which basically covers all the ground that you need in a much more concise way in the communications of ACM, which is open access. The nice thing about denotational semantics is that actually you don't need to know anything about the foundations in order to write or read a denotational semantics. Somehow it's got a reputation of being quite scary these days, and it's no longer taught in undergraduate curricula as it used to be, but I'd like to try and dispel that scariness. However, you do need a bit of meta-notation for defining the abstract syntax of a language, for defining domains, and for defining semantic and auxiliary functions. In the Scheme standards, they give you a little summary of what they think is the essential meta-notation to have in your mind when you read it, which is basically focused on the notation for sequences and omits to explain what plus or cross on domains actually is, but it doesn't really give you an introduction to the meta-notation. It assumes that you've already read Stoy's book, basically. The structure of the semantics is quite conventional: abstract syntax, domains, semantic functions, and auxiliary functions. For abstract syntax, it uses a grammar with sorts and also has meta-variables ranging over those sorts and productions. For domains, it names the domains and again introduces meta-variables that range over the values in the domains and gives the definitions just by equations, mutually recursive equations. The semantic functions have types which are generally mapping syntax sorts to domains, and then there's a semantic equation for each production that defines the denotation of that particular class of constructs in terms of its the denotations of its subterms. So now let's look at this shallow embedding and see how scary that is. Agda, as you may know, some of it's already been mentioned today, Agda is quite an advanced language, and I'm not going to be exploiting much of it in this talk. The main point that I'd like to highlight is that the arrow in Agda is used both for function types and for lambda abstractions, which is a bit off-putting if you're used to using a dot to separate your variables from your, or a parenthesis to separate your variables from your body. I must admit, the first time I started reading Agda specifications in Popple papers and things like that, it was one of the things that I was complaining about all the time, but I've grown used to it by now. So to start our shallow embedding in Agda, let's just cheat blatantly by saying domains are just types. So the universe of domains is the universe of types, which is called set in Agda. Don't think of these as finite sets, they're really just types. And we can introduce some meta-variables D and D ranging over domains. The really controversial bit comes with these two postulates. Agda users have been indoctrinated not to use postulates because postulates just can be automatically incorporated in proofs and, well, not automatically, but explicitly, and you have no sign that they've been used in the resulting statement of the proved proposition. This first postulate, saying that the bottom element is an element of D for arbitrary domains, means that that is an element of every type in Agda, and Agda includes an empty type. And to say that the empty type includes an element is blatantly unsound. However, that is not going to worry us at all. Similarly, for fix, we're going to say that for every function from an Agda type D to itself, that function has a fixed point, which is obviously nonsense. I mean, successor function or identity, successor function doesn't have a fixed point. Fortunately, the unsoundness of these postulates has no effect on the Agda type checker. The Agda type checker just goes ahead and type checks things, disregarding whether these postulates are sound or not. And that's what makes this shallow embedding work so well. There are plenty more postulates. In fact, one of the reviewers bitterly complained in the reviews about the lack of justification of all these postulates. You see, they're all over the place. You can actually abbreviate them a bit more in Agda if you want to, but I've done it on a line-by-line basis to emphasize how many there are. But this is just the standard domain notation that one has operators for that, so you can use in equations. Now let's look at the various pieces of the shallow embedding. So for abstract syntax, this is how it looks in the notation used in the Scheme standards. It's been the fixed notation in all the standards, with something that looks pretty much like a BNF grammar, as is pretty close to what is used in Stoy's book or in denotational semantics generally. The Agda embedding is something I'm less happy about. It's not as direct as I would like it to be because Agda does not support these kind of grammars that we use in denotational semantics. There are also a couple of irritations. Agda doesn't have implicit coercions, so we need to have explicit constructors for constants and identifiers. And Agda doesn't even allow you to use ordinary parentheses as notation for constructors. So I'm using banana brackets. And just, it doesn't allow to have adjacent holes in constructors, or one needs to have some terminal symbol or concrete token in between, and I'm just using something that looks like a space in the standard Unicode. But otherwise, it's a one-to-one correspondence, and rather than using meta-variables, we actually have to use the types of the arguments in the specification. Now let's look at domain equations, which are a bit more interesting. And these are the domain equations from the 5th revised report in the Denotational Semantics of Scheme. And the Agda version has basically an equation for each of the equations in the original that looks pretty similar. It's using pluses and crosses and things like that. Except that I've commented out one of them, the one for expressed values, because that Agda doesn't like cycles between type definitions, especially if they're constant types. It just goes into non-termination in the type checker. And so we have to break that loop somewhere, and that's a very convenient place to break that loop because we can exploit the injections and projections between that sum type and its semands, we have to use those anyway in Agda and in the Agda embedding, and we'll be able to get between those semands and E just using those operations that we'll introduce in a moment. For all the meta-variables and the names of the domains, it's a bit more tedious, and we're also distinguishing between the set MISC of miscellaneous values and the flat domain that's constructed from it by adding a bottom element. These are the injections and projections that we're going to make explicit. So let's see how it looks. I hope this convinces you that it's a fairly shallow embedding. You see the version from the report at the top, and at the bottom you see the Agda version. Okay, the dot has changed to an arrow, and we've had to insert spaces between our Greek letters to stop Agda thinking that there was multiple letter words. And we've also incorporated the double bracket notation in the operator symbol, the mixed fix notation for the semantic function. But really these are very trivial changes, and otherwise it's an on-the-nose shallow embedding. So this is of course, I've chosen on the slide the simplest possible semantic equation. There are some much bigger semantic equations in the Scheme standard, and you'll find that actually they also translate very straightforwardly into lambda notation. So there's also some auxiliary functions. We see the function truish that's defined here. We'll come back to that in a moment, but let me just say that for many of the auxiliary functions, again, the definitions, it's delightful with Agda that you can just use exactly the same notation for introducing the name of the function, giving its type, and then giving it an equation that defines that. Well, almost. So look at the definition of list. Well, that's a very neat definition in the original standard. It's not quite so neat here. First of all, there is the recursion on list in the denotational semantics, which is perfectly okay. You can define functions recursively. We define our semantic functions recursively. Also, auxiliary functions can be defined recursively. But in Agda, if you define a function recursively in terms of itself, then it has to be inductive, so that the type checker can terminate and know that you're not defining a non-terminating function. So we make an explicit fixed point here, which doesn't actually cost us very much. We just have to introduce a separate name and an explicit fixed point operator that's highlighted there. Moreover, in the auxiliary function definitions in the standard, it's rather haphazard whether functions are defined before they're used or not. Again, that's something that you don't really care too much about in denotational semantics, the order in which definitions are given. It's just a big mathematical definition. As in mathematics, you can just either do top-down or bottom-up or mix or whatever. So it's not wrong in the standard to do that, but Agda is very much a declaration before use language. So you can define things mutually recursively, providing you declare them all first and then give all the definitions afterwards. So had to move the declaration of cons before the definition of list. So it's not entirely a bed of roses, but it's not too bad. And finally, there's a bit of noise with going from an element of an ordinary aggregate type set that's not intended to be a domain to a domain and then injecting it in the sum. And that's where we exploit these injections between the semands and the sums. But Agda would require that injection to be made explicit anyway. The eta there is the thing that takes an element of an ordinary set and gives you an element of a corresponding lifted domain. Now to the wellformedness issues, getting near the end. I can't give you a definition of what wellformedness is for denotational semantics. It's a mathematical notation. It's not precisely defined. So I'm going to show you some examples that you may or may not agree with. I'm not sure whether this is a wellformedness issue or not. It's overloading in the Scheme standard. False and true are declared in two different domains. And when you look at the definition of truish, then you may get a bit confused about which domain you're talking about. And in fact, there's also another bug in that definition. You're not allowed actually to test whether an element of the expressed values is equal to something else because that is a higher order domain, and you can't have a continuous equality test on a higher order domain. So really you should project the epsilon that stands for the a value in scheme onto the domain of miscellaneous values M, and then test in that domain, which is a flat domain and has a continuous monotonic equality test. So there are a couple of issues there. Ironically, there's also an issue with the definition of the auxiliary function that's called wrong, which I found a delightful irony. Wrong is used all over the place, applied to strings. And that's the type of wrong. And that's not compatible, at least Agda doesn't think it's compatible with leaving X unspecified. X is not guaranteed to include strings. So I think that's really a genuine well-formedness issue. When I was about to submit the paper for the workshop, I was thinking maybe I'll just manage with the auxiliary functions that were actually used in the semantic functions and leave out the ones that corresponded to standard procedures, in particular this call with values. But then I had a bit of time before submission deadline and spent a couple of hours converting the scraped Unicode characters from the PDF into Agda and inserting the spaces and getting it type checked. And to my delight, the very last one I checked had a bug. Do you see what the bug is? Many people have probably looked at this and ignored the fact that K, the kappa argument, is simply ignored and thrown away. There's a typo that was, it should have been added as an extra argument in the highlighted part there. So this shallow embedding idea has some utility, let's put it that way. There are some more obvious problems with well-formedness. In particular, the compositionality is abused. Both of these, the second one is rather innocent, you just expand it out. The first one is really serious. You can get around it. There's a suggestion in the paper for how to do that. I'm not going to go into that here. The final thing I'd like to say is that, let me just put up that penultimate slide completely, that the definitions in continuation passing style sometimes start using stores, mixing direct style and continuation passing style, which is extremely messy. You can redefine this cons auxiliary function very concisely using continuation passing style, and it looks much nicer, and that's the way it is. So my final slide, conclusion, we have a shallow embedding. It reports those issues that I've mentioned, and there's an artifact that you can look at if you like. I hope you will. And it would also be very easy to update that 5th revision to the 7th revision and fix the bugs there. And what I'd like to know from this community is if there's any interest in continuing to have a denotational semantics in Agda. And anyway, thank you for your attention so far.
Any question here? Oh, lots of questions.
So speaking as an editor for R7 and R-Small, I'd like to apologize for our job in denotational semantics and also recruit volunteers for R7 and R-Small.
Yeah. Thank you.
So this well-formedness thing that you can check is basically internal consistency of the spec as written, and I can see how this works out with, even though all of these things are postulated. But can you use this formalization of the spec to then actually prove things about progress?
Thank you for the question. That's a very good question. So for Scheme, I've only done very little in proving denotations are sound in relation to what you expect to be the results of running the programs that you expect, that running 2 + 2 gives you 4 and things like that. For simpler languages, I have 3 examples that you can find if you follow my if you follow the links from this topic on my webpage, there's the pure untyped lambda calculus with the D-infinity model. There's Plotkin's PCF language, and there's the SCM language that's from this paper. That's the simple basic language that are on the website. For the untyped lambda calculus and for PCF, I do have examples of where the using the embedding, you prove various equivalences between denotations, and as far as I can see, that's the proofs are just REFL in Agda. You don't have to spell out the proof. The trick is to add some equations as rewrite rules. Agda allows that. By the way, that's a good reason not to use module parameters, because module parameters can't be used as rewrite rules. Postulates can. When we have, for instance, in the model of the untyped lambda calculus with D-infinity and an isomorphism or bijection between D-infinity and the function type on D-infinity, then when we get pairs of compositions of those two parts of the isomorphism in the denotation, we want to carry on the computation by eliminating the bijection going backwards and forwards between D-infinity and its function type. And with that rewrite rule in Agda, then you can do quite a lot of computation. But in general, it's rather skating on thin ice to be using potentially unsound postulates as rewrite rules in Agda. But so far, so good. Thank you for the question.
And maybe, last question. Just okay, maybe another one. I see some frantic waving.
This is short. There's not even a question mark at the end. There is every so often discussion on the R7RS small mailing list about nits here and there that might not actually be quite right and need to be. So my short answer is yes.
Okay. So in any case, I must admit I haven't been. I browsed a bit one of the mailing lists, which led me to the work of Anton van Straten with an executable version of the scheme semantics that was written in 2001. The website had disappeared, but I managed to retrieve it from the web archive. And interestingly enough, I found as a comment in his code, in his scheme code, I found a comment that he'd also noticed this bug in the definition of call with values, CWV, and I hadn't looked at his work before I'd found it using Agda, but it was nice to get confirmation that I was curious if he had a valid implementation of Scheme, why hadn't he found that himself? So he found that in 2001. I'm not sure it was ever reported or discussed on the mailing list, but it was only the mailing list that led me to his work.
Well, thank you for lifting it from commenting code to something.
Thanks, Peter. Great talk, obviously. It's great that you wrote that paper, but the perception of denotational semantics seems to depend on the person who is talking about it. If we look at like Dave Schmidt or Glenn Winskall or Samson Abramsky or this kind of guys, they say denotational semantics is really about domain theory. And boom, then we are started with the way domains are constructed and the way the mapping from domain to domain is continuous or not. And so there is tons and tons and tons of work about that, which you just say, oh, just consider domains as types. And an example of that is when I was reading your other paper and I had a question, I thought there was a typo. Then you told me, no, the bottom is implicit in the domain. You didn't explicitly lift the domain, so it is okay as is. So that's something that I clearly still don't understand. So the saying that the domain is just a type and then you can happily go and write, that exactly corresponds to the original semantics of Scheme, which was machine implemented and then mapped into LaTeX. Yeah. So that means that the original semantics of Scheme was ostensibly denotational because it was formatted in LaTeX, but there was no domain content, except that Will is an expert in domain theory. He did his PhD thesis with power domains, non-determinism, and that kind of things. Okay. So I still have a
let me answer a bit of that to start
yes,
with, before you continue.
I was done.
So, yeah, basically, what I'm doing is parametric regarding all the different flavors of exactly what domains are. If I'm going to reason about loops and recursion, then I should probably need to use Kleene sequences or limits of chains, at least, of approximations, and the approximation order will need to be explicit in the reasoning. So postulating also the order and its properties will be part of the postulates. The second thing I'd like to say is that in 1980, Dana Scott had a proposal for synthetic domain theory, which was getting away from all this classic set theoretic construction of domains as CPOs with particular carrier sets and partial order relations and completeness properties, which if you represent it in Agda, as in the type topology library, where you find very carefully developed definitions of domains, there you have a lot of work to do with continuity proofs all over the place. Now, Scott's idea in synthetic domain theory was that in constructive logic, you can get away with assuming that all functions are continuous and therefore have fixed points, and that all types are domains. Now, that's not compatible with Agda as it stands, because not all types need to have bottom elements. But if we can at least find some middle ground where we can go away from these blatantly unsound postulates and end up with postulates that correspond to a version of synthetic domain theory supporting both domains and so-called predomains, which are domains that don't need to have a bottom element, that could be an ideal way of getting a sound version of what I'm doing implemented in Agda, and that's my next project before I really retire.
May you never retire. Still a last point in my paper, in your festschrift, there was a facetious paragraph about the jungle of semantics of Scheme, and I was listing 15 papers that were specifying call-CC, all in different ways. And the question was, in all this jungle of semantic artifacts, which one is the real call-CC? And then I proceeded to interderive all these semantics, which made some enormous assumptions about simplifying. But then I could touch all the semantics, and then there was not, here is my semantics, and that's the semantics of Scheme, and here is your semantics, your semantics of Scheme, and which one is the semantics of Scheme? When do we know? And so like full abstraction, Allah. Okay. Is there a full abstraction between the denotational semantics of Scheme and the published operational
I've never
subscribed
to the doctrine that you should go for fully abstract semantics. It becomes so complicated. And the intention of denotational semantics, in my view, is to express the intended understanding in terms of representation of programs in terms of pure mathematical objects, values, without invoking an abstract machine. Strachey all the time was objecting to Landin's approach, where Landin had an abstract machine in the background to evaluate his lambda expressions. Mm-hmm. Strachey wanted pure lambdas, and from the beginning of the 60s was working on that. And I think that what I hope I'm doing is essentially making Strachey's original vision viable in Agda.
And that's super honorable. However, if we take Landin's operational
semantics... I'm sorry. Why don't you all take this to the coffee break?
Fair enough.
I think some of us, need to get going. But thank you very much. Let's thank Peter again.
Thank you.